Good evening, everyone. So I'm very pleased and honored to be here today to talk to you about Exoplanet after this weird and impressive introduction. I'm going to first talk to you about exoplanets, how we find them, and then maybe we will come back to aliens afterwards. So let's start. Each of us, I think, is amazed by this view. The stars have always been fascinating to human beings. And since the Copernican Revolution, we have acquired the certainty that they are not just dots of lights that we can look, that are kind of background for us. They are other suns. And, well, personally, since I'm a kid, I'm fascinated by the possibilities that there could be life out there around other suns. And maybe that by the possibility that these forms of life, some of them are even more evolved than we are, we could communicate with them and so on. But to search for life elsewhere in the universe, we had to start by somewhere, and we started, of course, by our own planetary system. We studied it in great detail. We had some thought and fantasy about the possible existence of life on other planets of our system. So you have here the structure of our planetary system, the solar system. And you can see that close to the sun, you have 4 small worlds, 4 planets that we call terrestrials, that are mostly made of rocks. And then further out, you have giant planets. So you have the gas giants here, Jupiter and Saturn, basically big ball of hydrogen and helium. And you have the ice giants, Uranus and Neptune, that are enriched in ices, but have still a big envelope of hydrogen. Of course, here the scale of distance is not at all correct. The planets are not so close to the sun, but the scale of size is correct. So you can see how small the Earth, for instance, is compared to the giant Jupiter, and tiny compared to the sun. So when we studied the solar system, we understood, pieces by pieces, step by step, that the Earth was very special. Our world is the only planet of our solar system that hosts water in liquid phase on its surface. And you can see this water, these oceans, in such nice images taken from space. And this water makes the difference between a sterile world and a world that can host life as we know it. All forms of life on Earth use water. You have here cells. All the cells are composed in a large fraction of water. Water is really critical for life on Earth. And this is our definition of astronomy of an habitable planet. So it has nothing to do with humans, habitable by humans. In astronomy, we call habitable planet a planet that hosts liquid water on its surface. And by extension, we hope that it could host life as we know it. And if you look at the Earth, you can see on this image that water is really nothing compared to the whole volume of the Earth. In terms of mass, it's 0.02% of the mass of our planet. And still, this small droplet makes the world difference and makes our planet habitable and even inhabited. So if we look at our solar system, we know that if we put a planet like the Earth too close to the sun, of course, water will evaporate. And then you lose this capacity to have liquid water. And if you go too far, water will freeze. So intuitively, you can understand very easily the concept of habitable zone, which is the range of distance to the star, to the sun, for which you can have liquid water on a rocky planet. And it is represented here by this green annulus. And you have, in our solar system, you have 3 planets that are close or within the habitable zone. So Venus is at the inner edge, Earth is within, of course, and Mars is within too, but at the outer edge. Of course, the edges are not so easily defined. They are model dependent. It notably depends on the assumed properties of the planet. It depends on the atmospheric composition of the planet, and also it depends on the models that you use to compute the surface conditions. Because what really imprints the condition on the surface of the planet is not only the distance to the star, but also the atmospheric composition, and notably the greenhouse effect. The greenhouse effect is this effect of the atmosphere that traps the heat from the inner layer and from the ground and keep it around the surface. And on Earth, we have a moderate greenhouse effect. We can have much larger greenhouse effect, like in the case of Venus. So studying the solar system, at the beginning, in the 19th century, we were dreaming of life on Venus. We were dreaming of life on Mars. Now our view is much more pessimistic. We know that Venus is a real twin of the Earth in terms of mass, of size. But you can see that even when you look at the images here, you can see that it's a very different world. And by studying it, we understood that it was enshrouded by a very massive atmosphere. The atmosphere of Venus is about 100 times denser than the one of the Earth's. It is composed mainly of CO2, which is a powerful greenhouse gas, and it translates into conditions at the surface where you have high pressure and very high temperature, around 400 degrees Celsius. Furthermore, it's very acidic, so it's clearly not the place to be if you want to have nice holidays in the solar system. And on Venus, there is no liquid water. In fact, the planet is thought to be completely desiccated by this greenhouse effect. After billions of years, water is gone. There could be still some water, but in the inner part of the planet. But even close to the surface, there is no more water. And then you have Mars, which is in the habitable zone. But unfortunately, Mars has the opposite problem than Venus. It has a very scarce atmosphere. Its atmosphere is about 100 times scarcer than the one of the Earth. It's also dominated by CO2. And because the atmosphere is so scarce, you have temperature at the surface that are very, very cold. You don't have enough greenhouse effect to make possible this existence of liquid water. The pressure also are too low to have liquid water, which is stable on the surface of Mars. And we know that Mars, within its first billion years, at an era, a time where it had liquid water on its surface. We are now sure of it. It was an habitable planet at that time. The whole question is did life emerge on Mars at that time? So there are missions that are planned to figure this out. But Mars now is clearly not an habitable world. So if we want to find habitable worlds like the Earth, we have to look much further away. Basically, we have to look to the stars. And this is a very difficult exercise to find planets around other stars. We call this exoplanet, extrasolar planet also. Their possible existence was already speculated back during the Copernican Revolution. So soon after Nicolaus Copernicus proposed that the sun was the center of the universe and that the planet, including the Earth, were orbiting around the sun, some philosophers like Giordano Bruno here, who came alive, who was born a few years after the death of Nicolaus Copernicus, proposed that the stars, and it was really visionary at the time, that the stars were suns, and that these suns, these other suns, could also have planets and even habitable planets. And even the great Isaac Newton, that put into equation the mechanics of the planets, the motion of the planets, and even initiated what we call modern physics, he also thought that the stars could have their own planets. But the problem at that time is that from a technological point of view, this was totally impossible to detect these exoplanets. And they already noticed it at that time. A great physicist, another great physicist, Huygens, made some computation, can we detect this exoplanet? And his conclusion was, no, absolutely not, it's impossible, because the stars, if they are suns, are so far away that it would be impossible to detect these planets. And still, technology developed from step by step during the centuries. And at the 19th century, the telescopes, the astronomy was developed enough for some astronomers to dare searching for exoplanets. And it's pretty surprising, but already in 1855, there was the first claim of detection of an exoplanet by this, well, English military astronomer. He was based in Madras Observatory in India. And by observing the motions of nearby stars, he concluded that one of them had its motion perturbed by an unseen companion, for which he proposed a mass, he inferred a mass compatible, consistent with a planet. This announcement, this detection was shown to be false, unfortunately, and many more followed during the end of the 19th century, and during the 20th century, there were plenty of exoplanet detection announcements, and all of them were not verified. They were discarded by further observations, because it's very difficult to detect these planets. And in the 20th century, in the first part of the 20th century, there was even some pessimistic view on the possible existence of exoplanets. Real guys like Isaac Newton and other people from the Copernican Revolution thought it was likely. Some theoreticians in the 20th century, at the beginning, proposed a model of the formation of our solar system for which the existence of exoplanets would be extremely unlikely, because this model was based on a near collision between the young sun and another star. So the universe is full of stars, but they are very far away from each other. If you take the galaxy, our galaxy, the Milky Way, the mean distance between stars is expressed in light years. 1 light year is 10,000 billion kilometers. So generally, stars are very far away from each other, but by pure random motions, you can have one star that passes super close to another. And in this theory, the collision theory, you could have some material that was attracted by the other star through the tidal influence of the other star, which was taken by the gravitational field of the other stars, and that would end up, it would be a kind of filament that would be taken from one star, that would end up in orbit around one of the two stars, and they didn't know exactly how, but these filaments, they suppose that they could form, at some point, planets in orbit around the stars. And so, in this scenario, exoplanets should be extremely rare. This kind of collision you can have around 1 or 2 per 100 or 1 billion, 100 million, so 1 billion stars in the galaxy. There are 300 billion stars in our galaxy, so this is something that is supposed to be super rare. In this case, detecting exoplanets is hopeless. Then, after World War II, a new theory emerged for the formation of our solar system. The collision theory was discarded because it has many flaws. And the new theory, that was in fact an old theory that was called nebulous theory, that was revived by some theoretician in the second half of the 20th century, proposed that the stars formed from the collapses of a big cloud, a part of cloud of gas and dust. So this kind of clouds are called molecular clouds. There are plenty of them in the galaxy. And through the gravitational influence of the environment, you can have a part of this cloud that collapses on itself under its own mass. And it will become denser and denser, and the center of this collapsing cloud will become hot enough to become a star, so dense and hot enough to become a star. And the rest of the material will make a disk like this, a rotating disk around the protostar, the young star. And in this disk, in the new theory, you would have the dust particles that would aggregate, that would collide, aggregate, form small pebbles, then rocks, then what we called planetesimals, so things like an asteroid in terms of size, and then bigger and bigger bodies, and then at some point you form the planets. So this was a new model for the formation of the solar system. And this was only a model until came to life the Hubble Space Telescope that you have here, that was launched in the 80s. And Hubble observed young stars, and it was followed by other telescopes from the ground. And observing these very young stars, it could be shown that all of them, or nearly all of them, were surrounded by a disk of material, of gas and of dust. And so you have here a panel of such what I call protoplanetary disk, and it was a real confirmation of the theory of this formation, possible formation of exoplanet in this disk. But what was remaining was the first detection of a real exoplanet. So it was also possible that in most disk planets were not forming. And so came at that point, in 1992, a real big surprise, the first detection of exoplanet after centuries of tries. And it was a huge surprise because these planets were not detected around normal stars. They were detected around a pulsar. And a pulsar is it's a neutron star, so it's the remnant, the corpse of a massive star that, so massive stars have a short life, well, for a star, because stars have a long life, but for a human being it's very long. But still, the more massive a star is, the shorter is its life. And massive stars have a very spectacular end, which is called a supernovae. And what remains after the supernovae is a super dense object, which can be a black hole if you're massive enough. If not, you have a neutron star, so an object smaller than the Earth and super hot in a weird exotic state. And one of them, which was in the category of pulsar, showed to be orbited by two planets. So what I show you here, and for all exoplanets, except a few, the figures are just artistic view. We are not able to do this kind of images, unfortunately, for exoplanets. And so it was a total surprise, and because of the exotic nature of this star, of this neutron star, the mediatic impact of the discovery was quite low, in fact. Some were proposing that these planets were formed after the supernova explosion, were not really planets analog to our planets in our solar system. And so the big discovery of a planet around a sun-like star was still awaited. And we didn't have to wait long, because it came only 3 years after. And it was done by these two Swiss astronomers, so Michel Maillot and Didier Queloz, that were observing a relatively small sample of nearby sun-like stars, and that discovered around one of them a giant planet similar to Jupiter. But it was again a surprise, and some were skeptic about this detection, because this planet, which is called 51 Pegasi B, this planet was very close to its star. So if you take Jupiter, it is more than 5 times more distance to the sun than the Earth to the sun. It takes 11 years to complete a revolution around the sun. This planet is only at something like 2-3% the Earth-Sun distance to its star, and it takes 4 days to complete its orbit. So it's super, super close to its star. It showed that exoplanets exist and that they can be very different from the planets in our solar system. At least it was the first in that planetary systems were maybe much more diverse than we thought. Because of course we were looking for solar systems. We were looking at the time for planets that look like our planet. And this planet came out of the blue like a bit surprise. And of course this was a big discovery, and it deserved to be, well, it was warranted the Nobel Prize in Physics, but maybe late in 2019, but finally it came, and it was well deserved. And it initiated a whole new field of astronomy, exoplanetology, the detection and study of exoplanets. And because of the big impact of this discovery, plenty of projects were initiated. More and more ambitious projects, more and more funding came to find these planets. And you can see the evolution of the field, the exponential evolution of the field in this diagram, in this histogram. So what you have here is the year. So the first planets are here in 1992. 1995, you have the first planet around a sun-like star. You have the cumulative number of detections. And you can see that it starts very slowly. Other planets are detected, let's say, by a few, a couple, or maybe a dozen, up to 2,000. And then the detection rate accelerates. And now we are at more than 4,000 exoplanets that have been detected by more and more ambitious projects. And thanks to the large size of this sample, we can draw very profound statistical conclusions on planets around the stars. And the first one, which is maybe the most important one, planets are everywhere. They are the natural byproduct of the formation of a star. Nearly all stars of our galaxy, and by extension of the universe, have their own planetary system. Secondly, the planetary systems are much more diverse than we thought. Our solar system is not at all the norm. And we know, for instance, that solar system twins represent something like less than 5% of the sun-like stars. The other 95% have different planetary system architecture. And notably, about 30 to 50% of sun-like stars have a system where you have planets of a few Earth masses, what we call super-Earth, up to the mass of Neptune, that are very close to the star. And we know that these planets could not have formed so close to the stars. They must have formed further out and then migrated inwards, when the disk, the protoplanetary disk, was still there. So you see here you have the orbit of Venus. Within the orbit of Venus, in this system, you have 6 planets very close to each other. You have planets that are super close to the star, even giant planets, the so-called hot Jupiters. You have planets around 2 stars, or you have planets that are in a binary system, triple system, quadruple system. So you can have planets that have 3, 4 stars in the sky. You have planets that are in orbits that are very elliptic. So unlike the planets in our solar system that have nearly circular orbits, it's not uncommon to have planets that are very elliptic orbits. You have free-floating planets. We have detected a few of them, but by doing statistical analysis, we know that there must be at least 100 billion planets that are free-floating in our galaxy. They were formed in a protoplanetary disk and then ejected by other planets or by a star, and they are just there, cooling forever in the interstellar void. And you even have planets around pulsars, so very exotic stars. I guess there are planets around black holes too, why not? Some things that you can find in science fiction. And among these 4,000 planets, we have a select subsample that are said to be potentially habitable. So it's only a few dozen of them so far. So these planets, we have measured their mass or their size. We know these masses or sizes are consistent with rocky composition. So these are probably terrestrial planets, and they orbit within the habitable zone of the host star. And the next step we would like to do to achieve is to study in detail this planet and search for traces of life on some of these planets. And I'm talking about the galaxy, just to give you some context. What is the galaxy? So our sun is part of a big cluster of stars that are all bound together by gravity. And this cluster of stars, if you could go very far away from it, you would see it like a big, big disk it contains about 300 billion stars. Stars in the universe are most often in such structures, so they are all linked together by gravity. And its diameter is something like 100,000 light years, where the typical distance between stars is a few light years. So you see how big it is, huh? And there are many, many stars in it. And it forms a nice spiral with several arms like this. You have galaxies that have different shapes, but our galaxy, which we call the Milky Way, has this shape. And we don't see it, of course, like this. We see it like this, like a band in the sky, when the sky is clear and there is no clouds. Something that is more easy when you are in Chile or Hawaii than in Belgium, but still, you can see the Milky Way even from Belgium from time to time. And we see it like this just because we are embedded in the disk. In fact, this band is composed of billions of stars. Okay, so how do we detect exoplanets? How do we study exoplanets? How do we search for life on these exoplanets? Well, the most elegant way to do it, and the most obvious way to do it, is to take a big telescope, make an image which has a very high resolution, and to be able to see in this image the star and the planet. This is called direct imaging, and it is technologically extremely challenging. But we can do it now, but it's very recent. The first detection occurred in 2005. Well, this planet is not really a planet, this is what is called a sub-brown dwarf, but okay, let's call it a planet. So this was really the beginning, and since then there has been many, many projects with many technological developments that enable to detect more and more exoplanets through this method. So you have the most amazing case here. You have 3 planets around this star. It is a nearby star that is more massive than the Sun. The star is masked here for a reason I will explain afterwards. So this is a method that is challenging, but it starts to work. Now, what we would like to do in the future is to be able to detect an habitable planet through this method. Let's say this one is habitable, and to study the planet remotely. So for this purpose, we're going to use a technique which is called spectroscopy. So spectroscopy is just taking the light of an object and spreading the light in different wavelengths, in different colors, like a rainbow that you can see on Earth. And doing so, we can learn about the composition of the outer layers of the body. Because in the outer layer of here, the planet, the light coming from the deeper layers pass through these outer layers, and it will be absorbed or scattered, and it will change the intensity, so the brightness at the different colors of the different wavelengths. And you will learn by studying this distribution of light as a function of wavelength, of color, the composition, and even the properties, the physical properties of these outer layers. Which means that we can, in theory, study an exoplanet light years away and learn about its composition. And if we do this for instance, Venus, in the infrared, so it is a spectral range of light that our eyes are not sensitive to. In the infrared, you can see a big structure here, which is a drop of flux that we measure in this specific wavelength that is due to the CO2 of the atmosphere of Venus that absorbs the light coming from the deeper layer. So just by studying Venus remotely, and it was done before sending probes to Venus, we could detect CO2 and reach a conclusion: the atmosphere of Venus is rich in CO2. It's the same for Mars, but Mars has a scarcer atmosphere. But if we do the exercise for the Earth, it's more interesting. We have other structures that appear that we can relate to water, and to here it's ozone, which is a byproduct of oxygen that is formed mostly by photosynthesis. So if we could do this for an exoplanet and reach this kind of spectrum, or this kind of data, we could infer, in theory, the composition of the planet atmosphere and maybe relate it to biology, to the possible existence of life on this planet. This is called a biosignature, spectral biosignatures. And the reason is that life alters the composition of a planet. So for instance, let's take this tree. So it's going to absorb during the day through its pigment, chlorophyll. It's going to absorb the light coming from the sun. It's going to pump from the atmosphere carbon dioxide. It's going to pump water through the roots. Water is going to be photolysed, so break apart by the energy coming from the sunlight. And it will release oxygen after breaking water, and carbon dioxide, using the energy from the process, will be combined all together to form complex organic molecules. This is how, basically, the tree is able to grow, to form material for its activity. It is its photosynthetic metabolism. And if we look at the evolution of the oxygen in the atmosphere of the Earth, we can see that around up to something like 700 million years ago, it was quite low. And then, because of the advent of photosynthesis, and because photosynthesis released a lot of oxygen, at some point this oxygen had nothing to react with on the surface or in the oceans, and it accumulated in the atmosphere. And now we have something like 20% of oxygen in our atmosphere. So if we can do this kind of composition measurement for the atmosphere of an exoplanet, we could be able to arrive to the conclusion there is photosynthetic activity, for instance, on this planet. But the problem with the direct imaging method is that I told you it's challenging, but when I say challenging, it's really super challenging. And to understand how challenging it is, you can look at this firefly here. So a firefly, if you put it kilometers away, it's very difficult to detect it, but you just need big glasses, basically. Big goggles, and you will be able to detect your firefly, to see it. But the problem with exoplanets is that they are very faint objects, but they are always super close to the host star on the sky. And the star, of course, here is this lighthouse. When you turn on the lighthouse, you don't see anymore the firefly. Because here the problem is not the resolution, the capacity to resolve one object from the other. It is a contrast between the star that is so much brighter, and I'm talking about millions or even billions times brighter than the planet. So how can we do this? Well, there is a natural way to do it, and it is exemplified by our moon. So the upper part of the atmosphere of the sun is called the corona. It's full of very nice structures like this. But you don't see, it's a plasma, in fact, that is bound to the magnetic field of the sun. You don't see it like this just because the star, the disk of the sun is so bright. But when the moon passes in front of the sun, and by chance it has exactly the same angular size than the sun, then you see very nicely this corona. So the contrast between the sun and the corona is decreased drastically thanks to this phenomenon. So we want to do the same for exoplanets, and I'm going to show you a small video that shows you the concept of a space mission by NASA that aims to do exactly this, so to hide the star, to see the exoplanets around it, and habitable exoplanets. So this is the telescope, space telescope. It has two parts. One is a classical telescope, and here you have what is called a star shade. You will notice it's flower shape that was designed specifically to reduce the noise coming from the star. So it's going to move very far from the telescope, something like hundreds of thousands of kilometers away from the telescope. In a very fixed position, it is going to put itself between the star and the telescope. And doing so, it will enable the images taken by the telescope to do not be polluted by the light from the star, and to see the neighboring and to see the planets. And with this concept, we could have a way to detect Earth twins and to study them and search for life on them. But unfortunately, this won't come before, let's say, 2 decades from now, if funding follows, because of course it is a super expensive space mission concept. It hasn't been demonstrated technologically, so we are not ready yet. And in fact, all the planets that have been detected directly so far are giant planets, so like Jupiter, but more massive, hotter, because the system is still young, and further away from the star. We are still very far by direct imaging to detect an Earth twin. Nevertheless, there is a possible shortcut, and this shortcut aims to use the fact that even if something is invisible to us, we could detect it indirectly. Like this invisible man here, you can see his shadow, even if you don't see the man, and so you can infer the presence, the existence of this guy. And we can do the same for exoplanets and for planets, through the mechanism of planetary transit. So a transit in astronomy is the crossing of a small body in front of a big body. So here you have Venus that pass in front of the Sun as seen from Earth. So Venus and Mercury are inner to the Earth in the solar system, and because all the planets are nearly in the same plane, which is called the ecliptic, from time to time we see Venus or Mercury passing in front of the Sun. So of course it enables astronomers to do nice images like this. And it's also a way for us to use the same mechanism to detect exoplanets. For exoplanets, we are not able to do an image like this of the disk of the star, because it's so far away. So we're going to use another approach. We're going to measure very precisely the evolution of the brightness of the star. And when a planet passes in front of it, as it will hide a part of its disk, even if we don't see the phenomenon, we don't see the crossing, we will see the brightness of the star that drops a bit. And then after the crossing, it goes back to normal. So what we do to detect exoplanets through this method is to observe plenty and plenty of stars. And from time to time, we see one that has a drop of brightness. And of course, this is a periodic phenomenon. So each orbit, the planet will come back. And from this mechanism, we can learn the orbital period of the planet. We can learn its size, because the drop of the brightness will really depend on the size of the planet. The bigger the planet, the deeper this drop of brightness. And furthermore, through other mechanisms, we can even measure the mass of the planet. And even better, we can study the composition of the atmosphere of the planet without any image of the planet at all. Because when the planet passes in front of the star, you have the thin annulus here of the atmosphere that will also pass in front of the star. And so you will have a fraction of the light of the star emitted in our direction that will pass through this annulus, and that will be not blocked, but that will be filtrated by the atmosphere. At some wavelength, you will have absorption. At other wavelengths, you won't have any absorption or scattering. And so by looking at the spectrum of the star outside the transit and during the transit, we will detect some subtle differences that come from that will be caused by the small signals coming from the planet atmosphere. And through this method, we can study the atmospheric composition of a transiting planet without any image of the planet. Now, the problem with stars like the Sun is that they are quite big. If you look at Venus, I told you it's a twin of the Earth in terms of size. Venus is really a dwarf, a dot, I would say, compared to the Sun. And so we want to detect the signal coming from the thin atmospheric annulus here. With current technology, it's impossible, unfortunately, because the fraction of the light emitted in our direction that passes through the atmosphere is so tiny, we won't be able to detect these tiny signals in the data that we will gather. So there is a very simple solution, is to move to smaller stars. And fortunately, the universe tends to make stars that are much smaller than our Sun. The Sun is quite a big star. Most stars in our galaxy and in the universe are so-called red dwarfs. And these red dwarfs are can be very, very tiny compared to the sun. And the most tiny ones are called ultra-cool dwarf stars, and these are the best target for the study of Earth-like planets. Because in this case, you have a star that is 10 times smaller than the sun, and you have signals that you're trying to detect that are 100 times bigger, because it relates to the square of the size of the star. And so in this case, if you do the math, you see that the signals that we should be able to detect are within reach of our technology. So we should be able to detect the atmosphere of an Earth twin if it was orbiting and transiting such a tiny ultra-cool dwarf stars. Another advantage of these small stars is that as they are small, also they are cool, much cooler than the sun. An ultra-cool dwarf star can be even twice cooler than the sun, and even cooler, in fact. And because they are so small and so faint, you have to put the planet very close to them to have the right temperature, the right irradiation to make possible the existence of liquid water. In other words, the habitable zone is much closer to them than for a sun-like stars. Which means that if these potentially habitable planets exist around these tiny stars, they should have very small orbital periods. So they should pass in front of the star much more frequently than a real Earth twin around a sun-like star. If you take the Earth and you want to detect the Earth by transit, you will have to wait 1 year between each event. And you have to observe at the right time when the planet passes in front of the star. It will last a few hours, and then you have to wait another year. So it's a very slow process. And to build up the signal to detect the atmosphere, it will take you centuries. Here it's not the case. For these ultra-cool dwarfs, the habitable zone corresponds to orbital periods of a few days, down to 1 day. So if these planets exist so close to the stars, it's easier to detect them for reasons I'm not going to describe, but also it's easier to study them through their transit because the transits are much more frequent. So now we have detected a few of these planets around ultra-cool dwarf stars I will talk you about later. And we need now a facility that would be able to detect the atmosphere of this planet and to learn about their composition and maybe to search for biosignature, to detect these spectroscopic biosignatures. And fortunately, this facility exists. It's about to be launched 2 months from now, so finger crossed, because this is really our best hope to detect the atmosphere of Earth-like planets and study their composition and hunt for biosignature in the next future. So it is called the James Webb Space Telescope. So it's a NASA telescope with a participation of Canada and Europe. And James Webb is the biggest ever space telescope built, at least by humans. And it will be launched. It's so big, in fact, that it doesn't fit in the rocket that will launch it. So it will be launched from Kourou in Guyane by an Ariane rocket, and it has to be folded in the rocket. And so James Webb will reach its destination, which is something like 1.5 million kilometers from Earth, in the opposite direction to the sun. It will stay there, and then it will deploy. It's going to take something like 2 months to deploy. There are 170 steps for this deployment. Any step that fails, it's over. So it's going to be super stressful. But once it will be deployed, because it will be deployed, of course, then we will have the capacity to study the atmosphere of these exoplanets. But there is a game to play before the launch of James Webb, which is to detect the best target for James Webb. And so there are two, I wouldn't say competing, but two synergetic projects that are doing just that, finding these right targets for James Webb. There is TESS, which is a NASA space mission that is led by MIT, which is composed of, it's a space telescope composed of 4 small lenses, and TESS is observing basically all the solar neighborhood, all the nearby stars, looking for transits and the hope to detect the best target for James Webb. And then you have Speculoos, which is a project led by Liège, hurrah, and which is a consortium. It is done in collaboration with other universities. It is much cheaper than TESS, and in fact, it is a different strategy. We are using ground-based telescope, which is much cheaper than space-based telescope, but they are bigger. It's much easier to have a big telescope on the ground than in space, because launching something even in space is super expensive. And we are targeting with this bigger telescope smaller stars. We are really targeting these ultra-cool dwarf stars. We have a catalog of only, nearly 2,000 targets, and we have been in operation since January 2019. TESS has started operation also a bit before in 2018. And so our strategy is synergetic because TESS is not able to detect planets around the ultra-cool dwarf stars. It's able to detect planets that are bigger than the Earth around stars that are bigger than the ultra-cool dwarf stars. Well, on our side, we really want to detect Earth-like planets, Earth-sized planets at least. But before launching this project, Speculoos, we had to basically acquire the funds to do it. And this is one of the main challenges for a scientist, is to get the money to make the project he has in mind real. So I decided to do a prototype of the project using a small telescope that I developed with my friend at Liège, Michaël Gillon. So this is called Trappist. You will see Speculoos, Trappist, you see that there is some similarities in the name. We always want to make some let's say, connection with our small country, because we are super proud, of course, to be Belgium. And we are not alcoholic. We like Trappist beers, but this is not the main reason of this choice. So Trappist is a 60-centimeter robotic telescope installed in Chile, in the Atacama Desert. So you can see how dry it is here. You don't see a tree. You don't see anything green. It's not Mars. It's really on Earth. The Atacama Desert is the driest place on Earth. It's super, super dry. It's a perfect place in high altitude, super dry and very quiet in terms of atmospheric turbulence. It's a perfect place for astronomy and very clear sky too. And using Trappist as a prototype of Speculoos, so drinking beers before eating cookies, we selected a small sample of ultra-cool dwarf stars to demonstrate that we had the capacity with a relatively small robotic telescope to detect Earth-like planets. And to our big surprise, in 2015, we did better than demonstrating we could do it. We did it. And so in 2015, analyzing data in my sofa an evening, I saw this thing here on my screen. So it's not super impressive. It's not an image from Interstellar movie or something like this. But for an astronomer, it's super impressive, really. It's really something big because it showed that in front of the star, something passed, and it had the right size to be an Earth-like planet. And so this star is in the Aquarius constellation. We observe it intensively. We studied the star itself. The star itself was only discovered in 2000 because it's super nearby. It's 40 light years away. Of course, when I say super nearby, it's an astronomer that is talking. 40 light years is not close for human scale, but at the scale of the galaxy, it's really very nearby. And this star was undetected until 2000 because it's super small. It has 10 times, it's 10 times smaller than the sun. Basically, it has the same size as Jupiter. And it's super, super faint. And so this star, we rename it TRAPPIST-1 to give it a more, let's say, sympathetic flavor. It has a very complex name coming from a catalog with plenty of numbers. We decided to rename it TRAPPIST-1, which is something that we could do following the rule of astronomy. And we observe and observe and observe again this star. And we detected transit after transit. And at some point, we had so many transits and so weird signals in our data that we start to feel the difficulty to conclude on this system. We know there were at least 2 planets, but we had hints of another one. Then at the end of 2015, we had hints of the 4th one. We observed even this weird event here. What you can see here is the brightness of the star drops drastically. then it remains quiet, then it drops again, and it goes back to normal through 3 steps, which indicates, in fact, that there are 3 planets that pass in front of the star at the same time, more or less. And so we knew there were more planets. We published our first result in 2016, and that we needed to observe continuously the star for weeks with a space telescope, because from the ground you are bothered by the night-day cycle. You can observe only during night, of course. You are bothered by the weather. You have plenty of gaps in your data. From space, if you have the right telescope, you don't have these gaps. And so we use an infrared space telescope from NASA called Spitzer to observe continuously the star. And finally, we could crack the system and show that there were 7 planets in orbit around the stars, all very, very close to the star. We observed during 2 weeks, and during these 2 weeks, we observed 34 crossings of planets in front of the star, 34 transits. And so finally, we had a good idea of the architecture of the system, composed of 7 Earth-sized planets. They all have more or less the same size, the one of the Earth. Well, in fact, 3 of them have the size slightly smaller, while 2, it's between Mars and the Earth. And what was really interesting in terms of search for life elsewhere in the universe was that at least 3 of them were in the habitable zone of the star. And we knew back then that these planets, because the star was so close and so small, these planets would be amazing targets for James Webb. Basically, the very best planet that you could dream of for James Webb. And we were hoping for 1, we had 3, and even the other ones are very interesting. So we had the gift of 7 planets coming, which was really amazing. And we can step back a little and think about these planets. Of course, we are still lacking a lot of information of these planets. So for now, we have measured super precisely their masses, their size. We know that from the densities that we measure for these planets, they are terrestrial. So these are not weird mini Neptune or things like this. They are really terrestrial planets. They are a bit less dense than the Earth, which suggests that they could be enriched in volatile elements. And we think about water. So we think they could be much richer in water than the Earth, which is something that fits the model for the formation of planets so close to the star. We think they form further out in an environment rich in water and then migrated inwards in a small train of planets getting all together close to the star. Now, what is amazing, it's nearly science fiction, but we can dream about the condition of the surface on these planets. So of course, we like to imagine water. You have here this what we are searching for, liquid water. But what is sure is that from the surface, you don't see the other planet like we see Venus or Mars, dots of light. You must see the other planet like we see the moon. So you must see the structure of the planet. You must see, I don't know, the continents, whatever is there, the clouds. Because the distance, the typical distance between the planets is only a few Earth-Moon distance. So they are super, super close to each other. You even have tides created from one planet to the other that are significant, that are relatively large. Not large enough to create super volcanoes, but still something that you could feel if you were on the surface of these planets. They are so close to each other, to the star too, that they must be what is called tidally locked, meaning that because of the gravitational influence of the star so close to them, they should show always the same face to the star. Like the moon to the Earth. The moon is very close to the Earth, and so it has been trapped by the gravitational influence of the Earth into this state where it shows always the same face. It should be the same for the planets here. So they should always have the same face towards the star. So you can imagine a face that is very hot, a face that is very cold, and in between a zone where maybe you could have a more pleasant environment. At least there must be some thermal contrast, significant thermal contrast between the day side and the night side. And if you have a dense atmosphere, you should have very strong winds from the day side to the night side, because the heat that is accumulated on the day side has to go somewhere, and going to the night side is an obvious solution. Also, the star itself is small, but it's faint. So if you look at the star from in the visible, so if you put a human being on the surface of a planet, it could look at the star without having its eyes burn in optical light. But from time to time, the star has what is called a flare. So it means it has a kind of photospheric explosion. On its surface, you have a kind of thermonuclear explosion due to its disconnection and reconnection of magnetic field lines. So these kind of stars evolve very, very slowly. Because they are so low mass, they evolve super slowly. They fuse very slowly the hydrogen in their core. The nuclear fusion in the core of the star is super slow. And the lifetime of these stars is much longer than the one of a sun-like star. So the sun has a lifetime of about 10 billion years. Here we are talking about 1,000 billion years. So you have ample of time around such a star. If you have life on these planets, you don't have to fear that you will end swallowed by the star. The star will stay like it is for billions and billions of years, nearly eternity. But still, these stars tend to be magnetically active. And they tend to emit a lot of X-ray, UVs. And because the planets are so close to the star, they are baked. They receive a large amount of X-ray and UVs constantly. From time to time, it's even worse when the star is very active. And it's possible that the atmosphere of these planets is constantly eroded by X-ray and UVs, also by charged particles, what we call winds, stellar winds. And so the existence of atmosphere around this planet is not at all secure. For what we know, it's possible that these planets do not have an atmosphere. It's really a question of, for instance, protection by a magnetosphere. We don't know if these planets have a magnetosphere or not. It's also a question of replenishment. So do they have volcanic activity that could replenish constantly the atmosphere? Or do they have a big reservoir of, let's say, water on the surface to replenish constantly the atmosphere? We don't know. So it's totally uncharted territory here. This is why we should not see this planet as Earth-like. The environment of this planet is totally unlike the one of the Earth. So, as I told you, there are amazing targets for Webb, for James Webb. NASA itself made some press release to outline how amazing these planets were for targets for James Webb. And what we hope to detect with James Webb, a few years from now, is this kind of thing here. So I'm not going to describe in detail what you see here. It's a spectrum, but it is the spectrum of the atmosphere of the planet. By the transit method, we could get such data with James Webb and to be able to detect water, ozone, methane, and so on. And in this case, what you have here is a planet that is inhabited. So you have oxygen that is in large quantity, which is seen by the presence of ozone in the infrared. And you have also methane. And in theory, when you have large amount of methane and oxygen, you should have oxygen that reacts with methane. And you should have methane that disappear quite quickly. You have such large amount of methane, you don't have any abiological possible source able to explain this methane, and you need some origin from biology. So this is what we call a chemical disequilibrium. This is what we are searching for. This kind of composition that translates into one conclusion: there must be some metabolism that is superactive on this planet. These planets have been so fascinating, not only for astronomers, but also outside astronomy. And this has been a very pleasant surprise for the team, is to see that Trappist-1 start to appear as a Google Doodle. Then we had some science fiction books. Then we had some songs about Trappist-1, video games about Trappist-1, comics about Trappist-1. And that was really a pleasant experience for us. You have to know that most astronomers are fans of science fiction. We need our imagination to be fed, and we use science fiction for this. And to see something that we discover translated into an artistic work is something really unique. So I talk you about Speculoos. Speculoos is no more a prototype. It exists since 2019. So we have 4 telescopes in Chile, in the Atacama Desert again. So notice, when I say it's dry, it's really dry. The humidity in the air is something like 1 or 2%. In Belgium, it's about 200 to 300%. Well, I'm a bit exaggerating, but you have one in Tenerife, and we have one in San Pedro Martir in Mexico. Of course, it's always pleasant destination for us, because we need a good weather, we need clear sky, so it's always in nice places. This is why astronomy, it's one of the reasons astronomy is such a nice job. Our telescopes are always in nice places. I can't resist to show you nice pictures of the telescope, just to trigger your imagination. So you have here Speculoos South, and you have the nice sky of the Atacama Desert. Here, this is a nearby galaxy. You have plenty of bright stars, faint stars, the Milky Way that is super clear. This is a drone view of the site. So what you have here is a very large telescope. It's a European telescope composed of 4 units. Each unit is an 8-meter telescope. It's the biggest telescope on Earth with these 4 units. And we are hosted by this European site. So we are a few kilometers from the top of the mountain here. We are here. And this view is interesting because you have another mountain nearby, and you can see that it is flat, which is not normal for a mountain. And it's flat because it has been bombed and flattened, and it's going to be the host of the extremely large telescope. So Europe is building the biggest telescope ever, a 40-meter telescope. It's the size of half a soccer game. And this telescope is also very close to Speculoos. So from Speculoos, we will see VLT and also this ELT telescope when it will be online around 2025-26. Here you have Speculoos North in Tenerife. You can recognize Tenerife here through the Tidally volcano. We hope that it will never wake up. As you know, in La Palma, you have some volcanic activity now, so it's a bit worrisome, but we hope that Tidally will remain quiet. And we have the telescope SANTEX, which is a reference to Saint-Exupéry, Little Prince, planets. And my friend Brice-Olivier de Maury from Bern, that is leading SANTEX, wanted to give it to have it look like the Little Prince. So you have the blonde hairs of the Little Prince and the color of his t-shirt, sweatshirt here on the telescope. So you see that astronomers can be poets too. And I'm happy to report that we have now a confirmed planet by Speculoos. So accumulating data from 2019, we have now detected a new system. We call it Speculoos 2 because Speculoos 1 is Trappist 1 because it was done by the prototype of Speculoos. So this system, we are still studying it. We still don't know how many planets it hosts, but we know at least there are at least 2 planets in this system. I can't tell you more, so right now. What I can tell you is the future is very bright for exoplanets. So after James Webb, so James Webb will have a lifetime of 10 years. After James Webb, you will have what is called the giant telescopes coming on light, ground-based telescopes like the ELT. So you can see how big it is. Well, you can see it because here it's a car. So you see, it's really a big telescope. And you have post-James Webb Space Mission concept, like this one, which is called ABEX, that will be totally dedicated to the search for extraterrestrial life. Unlike James Webb, James Webb is a general astronomy facility. ABEX will be totally dedicated to the search for life, for habitable exoplanet, and the search for life. But you will have to be patient to see ABEX in space because it's not funded yet. Now, I would like to, in this last part of the lecture, to talk to you about the next steps, but in the long-term prospects. So, we would like all to know what is on the surface of these planets. And through spectroscopy, I told you we would be able to decipher the atmospheric composition, maybe to arrive to the conclusion there is life producing, I don't know, oxygen, methane, NO2 or something like this, and that's it. It's a bit frustrating. So we would like to be able to send probes like we do in the solar system. Of course, it's much more complex, but still some brave or crazy persons are already planning to send such interstellar missions. So what you have here is an image, an artistic view of what are called solar sails. So solar sails are just like a sail, but the wind that pushes the sail is not the classical wind. It is the light coming from the star, the sun, for instance, or the light coming here from a laser. So you take a very, very powerful laser, you lighten this sail, and you will give it a very large momentum, enabling it to reach a speed which is not too small compared to the speed of light, in theory. And doing so, you could have one of these probes that reach the nearest star within, let's say, 10 to 50 years, which is still long, but given the huge distance, it's an amazing achievement. The problem is that for now, we are not ready at all to do this, so it's just a concept. If we do the experiment now, we will burn the sail because the laser will be so powerful. We need a super high momentum, so you will need a sail that is 100% reflective. We don't have such material that is 100% reflective, so even if you have an absorption of a fraction of the light, you will totally destroy the sail, which is not the point, of course. Also, it would be very difficult to send this sail in the right direction. It will basically simulations that show that it will go anywhere. And furthermore, the sail is super light. You need something super light. And the payload of if we call this a spaceship, the payload is only a few grams. So the instrument that you have to put on your spaceship is only a few grams. And these few grams have to be able to study the planet and send back some results, which is not obvious to me. So it's a first concept, but it's maybe not the best one. The best way to do so would be to send a real interstellar mission, something that has a significant payload. And for this, we need an energy source that we don't master, which is nuclear fusion. So you have here a concept of a nuclear fusion interstellar spaceship, which is called the Icarus project. Unfortunately, it's only a concept because we don't master this. So nuclear fusion is something that there's a large amount of work going on it, but we're still far from mastering it. And prediction says that it could take up to 1 century to really master it. And furthermore, even if we master it, you still need to fund such a mission that would cost basically the world economy of the human beings for one year, which is not so obvious to swallow. Huh? And you have to convince a lot of people to do so. So it will take a lot of steps to reach this level. Just to show you how gigantic would be the spaceship, this is the Saturn V rocket, the most powerful rocket ever built. Saturn V launched the Apollo mission to the moon. This is Icarus. And most of the mass is hydrogen contained here. It is the combustible of the mission. The payload is here on the head. Okay, so we are still dreaming of interstellar travel. We know that physically it's possible, theoretically, but technologically we don't master this at all. But we could imagine that, let's say, 1,000 years from now, we would master it. And going from there, we can reach the question, we can wonder, okay, we know that our galaxy contains 300 billion stars. We know, and thanks to exoplanets, we know it for sure now, that most stars have planets. And we can even have an estimate of the number of potentially habitable planets in the galaxy, which is something like 40 to 50 billion planets. So it makes a lot of places for life to possibly emerge and develop to something that is smart enough to to build a spaceship. So the question that was raised by Enrico Fermi, the famous physician when he worked on the nuclear bomb in Los Alamos, was the following. If it's possible to travel between stars, if there are so many places where life could have emerged, why don't we see traces of aliens? Why don't we receive messages or see spaceship in our solar system? Why do we seem to be so alone in the galaxy? And it is not, well, we call this a Fermi paradox, but it's not a paradox, it's just an observation. And because we don't have the data to answer this question yet, we can just speculate. And this question is made even worse when we consider the possibility to have drawn by artificial intelligence, which was something that was clearly science fiction at the time of Fermi, but now it's progressing very well. Now we can think about an interstellar probe that will be smart enough to reach a nearby system and to replicate itself. It will use asteroids or comets to find the material. It will build a small factory and makes copies of itself, like cells in our body, like living cells do. And in this case, these babies would go up to other stars, and you would have an exponential exploration of the galaxy. We call this von Neumann probes, because the idea was first drawn by a famous mathematician, von Neumann. And so the solution to this paradox, there are plenty of solutions, speculation about this paradox, but there are two ones that are maybe the most commonly accepted and most regarded that deserve to be discussed. And the first one is the one of the great filter. So let's assume that life is something that is frequent at the scale of the galaxy. We know that the evolution is done of living forms is done by natural selection. It's a Darwinian selection under the pressure of the environment. And you have kind of new steps, new solutions that are found to a new problem that is put by the environment. So life basically is trying every possible option, and the ones that work will make possible the survival of the species, and it will be well adapted. The others disappears. So you have a kind of random walk, and at each step of these chains of evolution, you have a new solution that is found. But it's possible that along the way that brought us from the first cell to humans, it's possible that there's been some steps, some jumps in this evolutionary process that was super unlikely. It was a kind of, I wouldn't say miracle because it's not the right term, certainly not in science to use, but it was extremely low probability event. You just need one such event. Let's say it had a probability of 1 over 1,000 billions. And if this is the case, then you could have life that is widespread in the galaxy, but you don't have enough stars in the galaxy to make likely the existence of another sentient species. This is the great filter hypothesis. I don't like a lot this hypothesis because it tends to make us special. You need this special step, this special evolutionary jump that would enable us to exist. And I would say it's kind of anti-Copernican. There is another one that is something that you can draw from the observation of nature. So we always think about aliens often like aliens like being wise, smart, gentle. They come here to look at our plants like ET and then they go away. But we could have another view based on biology, on environmental biology. So if you look at an ecosystem, at any ecosystem on Earth, you have, let's say, a food chain, you have a hierarchy from the prey to the predator, and on top of that you have what is called the super predator. So the super predator is always super well adapted to the environment, and it hunts not only herbivores, but it can also hunt carnivores. Basically, it eats everything. This super predator doesn't leave the competitors able to chase him. So this super predator, if you translate this in a galactic context, you can have the following scenario. So billions of years ago, so the galaxy is 13 billion years old. Our solar system is 4.5 billion years old. So you had plenty enough of time to have first civilization to appear, let's say 10 billion years from now. A few of them emerged, and one of them had a bit of advance on the others. And this civilization, because it's the product of natural selection, of Darwinian evolution, it doesn't like the competitors. And what it will do is just, it won't be a threat to the other species until they start to be potential competitors. In this case, our galactic super predator will erase all the others. So in this scenario, it's normal that we don't see anyone out there, because there is only one thing out there, something that is way too smart and advanced for us, that doesn't care about us because we are really at the low level of evolution of civilization. But if we start to be too smart, if we start to travel between stars, then we could hear about it. And I think we don't want to hear about it, of course, in this scenario. Which scenario is the right one? I don't know, of course. And this consideration led the famous science fiction writer Arthur C. Clarke to say that two possibilities exist. Either we are alone in the universe, and it's hard to be alone, or we are not, and we could pray to be alone. So both are equally terrifying. I don't want to finish on a pessimistic view, so I will tell you that life beyond our solar system has been a question has fascinated humans for centuries. It has been into the realm of imagination until now, but we are getting closer and closer to a scientific answer, and the answer could be even closer than we think. And I thank you for your attention.